So second law of thermodynamics here, we have the heat transfer, we have hot, C1 hot and C2 T2 cold. So we can say there exists a useful thermodynamics variable called entropy, which is like a measure of disorderness. Like, so a natural process that starts in one equilibrium state and ends in another will go in the direction that causes the entropy of the entropy of the system plus the environment to increase for an irreversible process and to remain constant for reversible process. It's always like most of the time change in entropy is like change Q over T. So we have for reversible process the final entropy and the initial is the same. So because we can reverse it to its initial state, but for irreversible process, as we cannot reverse them, we call this one the final disorderness is greater than the initial disorderness. So it's all about second law of thermodynamics. Concerning the second law of thermodynamics introduces the notion of entropy. Entropy means a measure of system disorder or messiness. U is the quantity of system energy, S is the quality of system energy. So I want you to have in mind, we were talking about in the first law, U, it is the quantity of a system energy, but S is the quality. So we have two things, the quantity and the quality of a system's energy. So you have to have in your mind, when you are talking about internal energy, it is the quantity of a system energy, but if you are talking about entropy, it is the quality of a system energy. For implication of second law, like let's say time marches on. If you watch a movie, how do you know that you are seeing events in order they occur? How do you know? This is a question for you guys. If I drop a raw egg on the floor, it becomes extremely disordered, greater entropy, right? If you can drop a raw egg. Playing the movie in reverse would show pieces coming together to form a whole egg, decreasing entropy, highly unlikely. I want you to think about these implications, like go for it. It's like a good analogy, but also interesting. And about direction of the process, the second law helps us determine the preferred direction of the process. A reversible process is one which can change state and then return to its original state. We said in reversible process, the final entropy and the initial entropy are the same, but in a reversible process, the final disorderness or the final entropy is greater than the initial entropy. So this is an idealized condition. All real processes are irreversible, but have this thing in your mind. This is just an idealized condition. All real processes are irreversible. Heat engine. Yeah, we will see about this heat engine later, but let me give you a highlight. Heat engine. A device which transforms heat into work is called heat engine. A device which transforms heat, we have heat, and that transforms into work, this device is called heat engine. This happens in a cyclic process. Heat engine requires a hot reservoir to supply energy QH. It requires a hot reservoir. We have QH, a hot reservoir here. And cold reservoir, we have a cold reservoir here, QC here. It defined as positive and QC is negative. This one is positive and so is negative, but most of the time we will see, so it delivers the amount of heat into work through this process, through the QH and QC. So we can have here the work done here. We'll see about heat engine later. Also cycles, read this by yourself, but it's beyond the scope of this presentation, but here we good place to elaborate on. We have Otto cycle, diesel cycle, Carnot cycle. Like these are interesting cycles. We were talking about this thing at the third slide or something about the cyclists, but read these pointers. They are really interesting. And the third law of thermodynamics is like you can get out. No system can reach absolute zero. This is one reason we use the Kelvin temperature scale. We use Kelvin. There is no Kelvin, 0 Kelvin, right? Yeah. Not only is the internal energy proportional to temperature, but you never have to worry about dividing by 0 in an equation. So there is no formula associated with third law of thermodynamics actually. This is really interesting. There is no formula associated with third law of thermodynamics, but we can say no system can reach absolute zero. This is the concept of third law. You can't get out. It's an analogy. So like, let's see, these are an example of open systems. We have hair dryer, we have here water heater, air compressor, shower mixer, ceiling fan, water pump, condenser, shower mixer. These are kind of open system steady flow device.